All right. So Nusselt's number is signified by a is a dimensionless number that is signified by an equation of 0.332 times Reynolds number to the 1/2 power times Prandtl's number to the 1/3 power. And what Nusselt's number is a ratio of convective heat transfer over conductive heat transfer. And we can show Nusselt's number through oops, it's not, a flat plate where heat's going to be coming in and hits a boundary. Blue, show the boundary. And that boundary is going to have a boundary layer and a length that will signify as x, as well as a distance signified by delta. There we go. Okay. And so our convective heat transfer over conductive heat transfer is going to be equal to hx over k, like kind of stated in past videos, where we have two of these values already within. And what we want to do is maximize our h. And h is going to be, or h is going to be this coming in. And how to maximize our h is we're going to break down this equation where we have the Reynolds number equation, which we learned in our past class of fluid mechanics to be diameter times velocity times density all over the viscosity, as well as Prandtl, another R, Prandtl's number equaling momentum diffusivity over thermal diffusivity. And breaking this equation down, we've learned thermal diffusivity many times where we have K over the heat capacity times the density. And then in the first homework, we went over this quickly. The momentum diffusivity is going to be viscosity over density. So simplifying this out, densities cancel, and we're left with the viscosity times the heat capacity over the thermal conductivity, equaling Prandtl. So plugging these equations in, we find that h x over k is equal to 0.332 times, we'll put in d to be x within the Reynolds number, dx, sorry, x velocity density times or over the viscosity, the 1/2 power times viscosity, heat capacity, and thermal conductivity to the 1/3 power. And isolating H, we throw K over X on the other side. And these two K's are not the same, as this is to the 1/3 power and this is to the 3/3 power. So simplifying it out further, you get that H is equal to, I guess simplifying everything, because we have X's and viscosities. You get the velocity times the pressure to the 1/2 over viscosity to the 1/6 times the heat capacity to the 1/3 times the, yep, simply the heat capacity to the 1/3 times the thermal conductivity to the 2/3 and X to the 1/2. And that being the denominator shows that for H, the the bigger the length, the bigger the length and the farther out it goes, the smaller this heat is going to be. Or heat transfer is going to be. So since we want to maximize it, we want the smallest possible length that we can get within that. So that is how to maximize the heat transfer over a rectangular flat plate.